Today we are going to talk about Chat with Handbook. Chat with Handbook is a project that I made for the internal conference of 2024. And in this presentation, we will see how to use large language model to build a chatbot that is able to answer on your specific documents. In fact, when I joined AgileLab, at the beginning, I had a lot of questions, and my buddy and my colleagues keeps suggest me to look for the answer in the handbook. But the process to retrieve to search information was so demanding and time costly. And on the other hand, I neither use ChatGPT because it's not able to answer to specific question like what is Agile Nomad, what mean EMP1, is the what is our health insurance. So for this reason, I built my own chatbot based on the handbook and using the OpenAI API. Today, I will show you how this process works from both theoretical and practical point of view. In fact, you will see also a little demonstration. Let's start with some problems with generical purpose chatbot. For generical chatbot in 2024, we're referring to GPT-4. That is a new generation of language model that is trained to look at these some sentences and try to guess what are the most probable next words. In order to reach this goal, OpenAI trained this model with all the open source text information over the internet. By doing this process, the model starts to acquire knowledge about the world from the documents that it saw during the training. So entire Wikipedia, some books, forums, New York Times article journals, and so on. But for this reason, it's not able to know, to have knowledge about specific company data that it never seen before. Like, for example, the terminology EMP1 that is specific of our data. Since it's possible to extend model knowledge by training, this process is pretty costly and slow, and also not so naive. For this reason, even OpenAI update its chatbot knowledge just once or at least 2 times per year. Since the handbook is regularly updated, this process can be very inefficient in our case. The third main problem with this kind of general purpose chatbot is the hallucination problem. What is hallucination? As I said before, these models are trained to guess the most probable continuation of a sentence. That means that the model is not trained to speak true. It's only trained to guess the most probable continuation of the sentence. And sometimes they can answer with a fake sentence. So it can produce an answer that it's similar to a real one, sounds good, but is actually not grounded to true facts, and is pretty impossible for us to figure out when a model is producing real answer and when it's not. We talk this problem hallucination. The last problem is the lack of ability to cite the true source of information from where the answer is derived. In fact, during the training, the model starts to create a mental model, about the world and is synthesize some fact, some information, but is not able to create a connection, a link between the fact acquired and the source of information from where the fact is retrieved. So if you ask during the at inference time, if you ask to prove, to demonstrate some information, it is not able to explain why and or where he he extract the information that is providing to you. Now, all those four problems can be addressed with retrieval augmented generation. Retrieval augmented generation just means allow the model to read your data before generating an answer. I left here an example for you. I ask to ChatGPT what is Agile Nomads. Then I append an instruction, so not just a question, but a more complicated interaction. A question followed by an instruction, and this instruction just says, please, before answering, read the follow-up documents. Next, I left the piece of documents extract from the handbook that contain the chapter about Agile Nomads. ChatGPT is able to follow my instruction, read the source of information about Agile Nomads, and generate this time a correct answer. So as you can imagine, this process can solve all those four problems because it's able to cite the source information because it's the one that you provide. Is able to keep itself updated as soon as you send update version of the documents. Is able to avoid hallucination because answer a question is a creative task. Instead, extract the correct information from a document and reformulate the text in order to produce a rephrased version of the extracted content is not a creative task, but is a more technical task. So if you complete the instruction to ask the model to do not answer if the correct answer is not present in the provided document, it will avoid to made up fake answer, and it will avoid hallucination. The last problem, actual, I do not. No, this is cover all the four main problems. The only problem now is, okay, that's great, but it missed the point if I need to retrieve by myself the correct document to allow the model to answer. Of course, the point behind the retrieval augmented generation is to automatize this process. In fact, retrieval augmented generation means augment the model context, the model knowledge, by retrieve the correct source information and provide to it before it has to generate the answer. In order to explain how we can automatize this process, I need to introduce a new main component, that is the embedder. There are two main models in the transformer family of neural network. The first one is GPT. It is a generator model that see a piece of text and try to guess how it continues, generating new text. The second one is the embedder. The embedder has another purpose. Everybody knows that our machine, our computer, our devices are only able to process numbers, binary numbers. It's not able to process text. Now, it's it's possible to map every words to numbers because numbers are infinite and words are limited. But it's pretty impossible to map semantics behind words to numbers. The purpose of embedder is to approximate these results. In fact, the embedder is a transformer, a neural network trained to synthesize, to encode all the semantics behind a sentence into not just a number, but into an array, an embedder, a multidimensional vector, usually more than 100 dimensions. Now we still have a problem. In addition to our machine, also the neural network are not able to naive process text, since they are just a bunch of numbers and matrix multiplication. So the problem is how you can teach to a neural network the semantics behind the words. The good news is that you do not you are not forced to do it. You can achieve the same result with a workaround or an auxiliary task. So you do not teach directly to the model about the semantics, but you can ask the model to solve a simple task that required a deep knowledge of the language to be solved. The task is pretty naive. You take a sentence, you remove random words from the sentence, and ask the model to infer what is the removed sentence. So the model will look at the surrounding context, all the words before and answer the removed one, and will try to guess what were the removed words. In order to solve this task, the model will start to create a mental model of what is the meaning of the removed word just by looking at the surrounding context. So, for example, we'll start to understand the syntax of a sentence, the relationship between a subject and a verb, then start to guess the synonyms of some words, the opposite meaning, and start to guess the different shapes of meaning behind each word every time it's the same word in different context. But even this is a very powerful model, we still have a problem. In fact, we want that model start to learn the difference between similar and different sentences. I mean, if we compute the distance between vectors, and we can do this with cosine distance um, that calculate a scalar a single value that indicate how the given vectors are similar or different. And we want that the model is able to produce different vector for sentences with different meaning and vice versa. We can force the model to obtain these results just by put the result of the cosine distance inside the loss function. So we take a sentence and we embed it. We take a similar sentence and we embed it. Then we calculate the cosine distance between the two embeddings, and we ask the model to minimize this value. Then we repeat the same process with a sentence and an uncorrelated sentence. And now we ask the model to maximize the distance between the two sentences. What we obtain at the end of this process is that the model is able to map into the semantic space all the sentences and will cluster in the same spot all the sentence with the same semantics. In order to allow you to imagine this process, I created this example where I take a query, a question, where is the Turin office located? I embed and obtain an embedder. Then I use a dimensionality reduction algorithm to compress the embedded the vector in a 2D vector. Then I plot the 2D vector like every dimension is a coordinated. So you can imagine the 2 dimension like the XY coordination. And you can see the plot, the dot that represent the sentence in pink that is indicated by the pink arrow. Then I repeated this process with other sentences from other documents. And in particularly, you can see that the two dots that are near to the pink one are sentences from the documents named Turin, and you can see in blue, while in brown you can see the sentence from the document named Bologna that is pretty far away from the pink one. Okay, now you have all the ingredients to the theory behind the neural networks. And now we can move on to the framework. As I specified in the title, I built this chatbot from scratch. I do not use open source framework like Langchain and Llama Index because I had not good experience when I worked with them, and also because I wanted to make some experiments with this pipeline, and I wanted to be able to customize every aspect of the pipeline. Lastly, I think that the general entity between this kind of framework are pretty simple, and now I will show you all of them. And for this reason, I think that it's pretty easy to rebuild from scratch this framework. So I suggest you to do it if you need to spend a lot of time with this kind of software. The main general concept is the knowledge base. Knowledge base is just a collection of documents. In our case, the handbook is a good example of what a knowledge base is. Knowledge base is a collection of documents. What is a document? A document is an entity, a class, with a link to the physical path on the machine and a list of chapters. Chapters are other entities with a link to the main document, and with a title and with a text. The text is then splitted into chunks, and every chunks is a piece of a linked list. So every chunks contain a pointer to the previous and to the next one, a pointer to the main chapter, and a pointer to the document from where it is extracted. Is also, in addition to links, it also has a text and the embedded version of the text, so the embedded vector. Now we have all the ingredients to create the Retrieval Augmented Generation pipeline. Actually, the pipeline is split into two main phases. The first one is the data ingestion, is a script to collect all the data behind inside the knowledge base. And the second phase is what happens every time we receive a query. So the data gathering starts in our case with a git clone and with a script that remove all the unnecessary file. In this case, it also has a markdown. It also left markdowns file and images file. In fact, in the second phase, we need to use parser to retrieve all the chapters and split all the text. And every time we encounter an image, we have to turn image into text with a large language model, and then parse and split this produced text. To turn image to text, I mean ask another language model to another language, a multimodal language model. Some of them are able to map the same concept to the same spot, even if the concept is represented with textual or image form. So we can ask the language model to look at the image and describe with a lot of detail the content inside the image. By doing this process, we are now able to index the content inside the image. Some embedder are natively multimodal, are natively multimodal. So for this kind of model, this process is not necessary, but for this project, I want to use a very small embedding. In fact, the embedded that I use is can run on my local machine and is very fast. So I do not need to use a big embedder and maybe on remote machine. So I prefer this solution. Then we will end up with some entities where each entity is a map, is a dictionary where the embedder from the text is the key and the value associated is the list of metadata. So text that produces the vector, link to previous and next entities, or also link to documents or chapters. The last step is to put all these entities inside a special kind of database named vector store, and we will see more details about it very soon. Okay, inference time. What happens every time we provide a question to our chatbot? The first things we have to do is embed the query. Actually, we can pre-process the query. For example, we can translate the question, or we can ask model to rephrase the question, or we can split the question into multiple questions, whatever. The only mandatory things that we have to do is at the end of this process create an embedding of the question, because we need to use a vector store. Vector store is a special kind of database that is designed to work with vectors. It contains vectors, and it requires to receive a new vector as a query, because it is optimized to calculate the distance between the query vectors and all the others. In this plot, you can see the blue dot that represent the query vectors and all the other vectors. You can see that some of them are more close to the query one than the others, because the content behind these three vectors are more similar, more correlated with the one produced by the query. So thanks to this process, we can find the chunks, the entities that are more correlated with our query. We can extract some text from these embeddings because of the metadata associated with the embedding. As I said before, every embedded is a key, and the value is the text that produces the embedding, the link to other piece of chunks. So the piece of text that is previous and next to the current one, and also map to the entire text, the entire chapter or entire document. So for example, you can just require all the text, all the documents text from the one that produced the most similar embedding, the most similar to the embedding. At the end of this process, you will end up with a situation similar to the one described at the beginning. So you have the user query, a list of documents that contain all the useful information that the model will use to answer the question. Now, since the vector store is able to indicate the most similar embeddings, you still need to choose several of them, because sometimes the correct answer is spread over different piece of text, and also you want to cover yourself from false positive results. So maybe um, the piece of documents that is result from for be the most similar or the most correlated can not can be the not the correct one. Maybe you can have false positive in the first position, so you have to choose more more document that strictly necessary. In my case, I extract a top 10 of the closest results. And then I send all of the 10 documents to GPT, and I ask it to producing an answer to not invent facts and just stick with the information provided by the documents, to ignore all the documents that contain data that are not related with the question. And basically, you can ask the model whatever you want, as soon as you will maintain a low effort in terms of money and time, because the more text, the more instruction you provide, the more the price and the time will increase. I show you now a real an end-to-end example where I ask a question, I retrieve the documents and produce the answer in streaming, so in real time. And then I also ask for additional information, for example, the name of the handbook page that contain the useful information to answer the question, and the specific chapter title inside the page. I want to focus your attention on the right parts, especially the retrieval time, to show you how the embedder and similarity search is fast. All the other time is due to the OpenAI response. Okay, before concluding this talk, I want to spend some words about optimization process. During the development of this chatbot, I have a lot of decision to make. For example, what is the correct algorithm to chunk to split the text into chunks? Maybe you can split every sentence. Maybe you cannot split. You can send all the chapters text, or you can split using the sliding window algorithm. That is the one that I used. Second problem is, okay, I have the algorithm, but what is the correct chunk dimension? What is the chunk overlap? What kind of embedder I should use, because there are a lot of embedding in open source world. And once I calculated the distance between query document and the others, how many of them I need to retrieve, and for each of them, how much text I need to extract. There is not a general rule to answer all this question. The only correct way to do is fit the best parameters to your specific data. And in order to do this, you have to treat this task like just all the other data scientist tasks, data science projects. So you need to create a dataset. You need to do some exploratory data analysis. For example, the distribution of the chapter's length or the document's length, and you need to create a matrix. For example, for this project, I crowdsourcing the dataset. I asked to all of you to send me some question. I retrieve 65 human question, and I also build some synthetic data with the GPT. I explain this process. For me, the dataset is composed by two columns, the question and the labels. The labels is the name of the documents that contain the answer to the question. So, for example, if the question is what I need to do what I need to go to a what I need to do to go a conference. The label is the name of the document that contains the answer for this question. In our case, the document page is named conferences. To produce synthetic data, I just take a page of the handbook, send to GPT, and ask to extract some question from this page. Doing this process, I will end up with some question and with the name of the document from where the question is extracted. About the metrics, I use the reciprocal rank that work like this. You take a question, you ask your retrieval method to rank all the documents in such a way that the ranker has has to put the correct document into the top of the list. You know what is the current document because it's the label that we saw the slide before. So you know where is the position of the correct documents. The matrix is just one above the position of the correct document. So in this way, you would push the model to put the correct document in the first position in order to maximize this value. And of course, you can repeat this process for all the questions and maintain a mean of the total results. Okay, I left in the left part of the slide the most sensible and most relevant parameters. And at the right part of the slide, small pieces of all the experiments that I made. And at the bottom left part of the slide, you can see the best configuration that I found. I want to focus your attention to the chunk size, that is 50, that is the number of words for each chunks. And is pretty small because the embedder is trained on sentences, maybe often singular sentence. So it work well with small portions of sentences, and also because it in this putting too much content inside every chunks will confuse the embedder because we will ask it to put a lot of semantics into the same embeddings. Instead, by having fine-grained piece of text, we can more easily separate them into the semantic space because every embedding is talking about one small things. The last things I want to highlight you is the embedder name. Because it's very little embedder, just 80 megabytes. Is a completely free and open source, can run very fast on Mac, Windows, and other machine. It works without GPU and is pretty powerful model. The last thing that I want to say is that we actually just saw the most simple approach. I actually tried more complicated, more advanced stuff. Some of them worked pretty well, like combine modern vector search and classic keyword search, like BM25 algorithm. Some of them doesn't work well. For example, try to add the name of the document to each chunks before embed them. and some others work well in some cases and bad in others. So at the end of the day, it's hard to say if the model, if the chatbot works better with or without them. But there are a lot of things that I haven't tried yet because of the times. And this led me to the last slide, that is um, a call to action for you, because I want to open source all my code, and I will glad if some of you will be interested into uh, take the source code and develop above it. And I want you know that it's not necessary to be a data scientist to work with this code. In fact, I need a lot more software engineering than data scientists, because the vast majority part of code that I have to implement is not related to data science. And so uh, I will um, um, I will create a repository in our AgileLab GitLab. So if you wanna participate, just contact me. And that's all. Thank you for uh, thank you for listening to me, and enjoy. Have a nice day. If you are a question, send it to me. I repeat, my name is Luca Sorrentino. Bye.